Okay, awesome. So I'm Katie Porfian, I'm a data scientist, and as you can see on what's being viewed right now, and that's live EEG data, and that's coming from my lovely assistant that accepted to wear the Muse headband. Now, this presentation is going to not be so much focused on the neuro, but how do you take a data set, something like this, that you may not necessarily know about, and build a prototype about that, and what are the steps that are required to go through that? So this is going to be focused on my personal project. And that's called BrainDrain, where I'm using brainwaves and machine learning techniques to detect errors in human problem solving. So this actually goes back to when I first started my undergrad. When I went to school, I decided I'm going to be a psych major. I took some courses in my high school, and I was like, yeah, this is awesome. And I took one class in college and realized this was not for me. So 7 major changes later, I discovered my love of computer science. But the idea of the brain and how it works stuck with me all those years. And that's kind of where, when it came to do my senior research project, which is a requirement at my university to do before you graduate, I wanted to do something with the brain. But in particular, something with student learning. I've been a TA and tutor, and my mom's also an educator. And so I've always been a part of the classroom. And so I wanted to do something with that and big data, but wasn't exactly really sure what should I do. And then I started thinking. I went to a lot of hackathons, and I remember seeing these EEG devices that people were using. And it made me realize there's a lot more medical products that are becoming open to the public, normally that you would only see in a doctor's office or a hospital. Well, the average consumer can use these products now. So there's an opportunity to really start developing in this field. And that's where I determined my goal. I wanted to develop a model that will correlate brain activity with problem-solving performance, and then use this model to, in turn, predict performance from brain activity. So that's a lot of big words. What exactly does that mean? Let's say someone's sitting there, and they're trying to figure out a math problem, start struggling. Well, a little notification pops up and says, hey, you might actually be going about this the wrong way. So it says in between the user and the notification of, hey, you might be thinking about this incorrectly, try going back. And it's this circle until they successfully solve the problem. So this is great and all. I have a goal, but I want to use brain waves and all these crazy things. I'm not a neurologist. I've barely haven't really even taken a neuro class. So I had to do some basic backgrounds. I just want to go ahead and say most of the research I've done has been thanks to Google Scholar. So just be wary and don't take the as 100% true. But there are 4 main brain types: the alpha, beta, theta, and delta. And I decided I wanted to focus mostly on the beta. And that's because that's where your active concentration is. This is where your problem solving is occurring. And it's really only dominant during those stages. Otherwise, it's your alpha when you're resting, and theta when you're starting to daydream, and delta is the most dominant in your deep sleep. So how was I going to collect this, though? So I decided on the Muse headband, which was released in the summer of 2012 and is currently marketed as a meditation assistant application. What is that? So basically, you sit there and you first off think about dogs or cats and sports, crazy things like that, and that calibrates the device. From here, you start thinking about your breathing. And if you stop thinking about it and start thinking about other things, instead of hearing nice, cool ocean breezes, a storm starts rolling in. And so the Muse headband already had that feedback capability, which is what I wanted. And the Muse headband, which you can see on Angelo, it has sensors in the front, and they go around the side to the back of your ear. And it also does jaw detection and eye blink detection. So it has a lot of capabilities, and it also gives me the 4 main brain types, and gives me something what the Muse headband calls raw FFT values. Now, if you never used fast Fourier transform before, think of it as it takes a signal, which is often in the space of time or just space in general, and it converts the signal into frequency domain. And the Muse takes this and automatically calculates a Hamming window of 256 samples that are slid over by 22 samples, which is about 1/10 of a second, giving you a 90% overlay. So all of this together with the raw FFT values that Muse calls is supposed to help reduce noise and try to get rid of any of that random static that the signal might pick up. So this is great. I have a basic background on neuro, thanks to Google Scholar, but is there any other research that has been similar to mine? And that's kind of the next step you should take. And that's where I discovered classification of patterns of EEG synchronization for seizure patients. Now, this study really stood out to me because they wanted to focus on testing different classifiers. So they took bivariate features in windows of 5 seconds, basically saying this user is having a seizure, they're not having a seizure. Pretty straightforward. Now, they concluded that the best combination with brainwave prediction was a convolutional neural network with a wavelet transform. So instead of using FFT, they said use wavelet. So I had most of my research set up, but it's kind of time now I need to do my actual methodology. How am I gonna build this model? Where am I gonna get my data from? So I decided I would monitor student brain patterns using the Muse headband and then train on brainwave values to create the model. Then I would develop an application to provide direct feedback. So gathering my data required doing experiments. So during my first experiment run through, I wanted to do something simple. I hadn't worked with an ETL yet for this and wasn't really sure how or what was the best way to set it up. So because of the Muse Lab, which you guys saw earlier, it's a Java application created for Muse developers. And what's really nice about it is that it automatically converts the signals into CSV, so it's easy to work with. So to make sure the timestamps synced up as closely as possible, I had to write this as a Java application for my experiment. And in this Java application, I was able to record whenever the question was shown and when it was answered, and also if they got it correct or incorrect, and exactly what the problem was. So that left me with 2 CSV files. On one side, I had my answer, which was the time shown, time answered, and if they got it correct. But then I had the Muse file, which was this very long file of just completely different things, such as is the elements is good, low frequency, absolute, a lot of stuff I didn't need. But I needed to merge this and just pull out the information I wanted. So I wanted to visualize this. I didn't know exactly what's in this data or what's going on with this. So RStudio is kind of my go-to when I want to do visualization, and especially because ggplot is so strong. So we're actually going to head into RStudio now. And I have these 2 data files already loaded. So here's my data ag. Now it might look a little different. So I went ahead and just aggregated and took the mean of all those signals. And you might see a lot of times it's 4. One is for each of the signals from the Muse headband. So I just took the mean. And then I have my other file, the answer, so whether they got it correct or incorrect. And I went ahead already and just added an indexed ID. So nothing too fancy. But now I want to start appending them. I'm going to go ahead and use lapply. And can you guys see that okay? Is that a little small? Oh, okay. I don't think I can make it bigger. Anyways, so I want to say take data arg and add this new column. It's going to be called question. And lapply, so for every row, take the data arg time and pass it into this function. And this function is going to take a subset of my answer where it says find where the times occurred between time shown and time answered in my answer folder. And you might be a little curious, why am I dividing it by 1,000? Well, if you go into the data arg, you can see it's pretty much a whole number. Well, Java did something a little interesting, and it made it into a decimal for my other file. So it may have been the same date time, but it just put it in a different format. So dividing by 1,000 helps correct for that. So I'm going to go ahead and run this. Sometimes it takes longer than others. All right, and then you have to unlist everything. So now I am left with a data set that should have a question on it. But you might be a little curious, why is there NAs everywhere? from just the head? Well, I start recording on the Muse headband prior to when the questions are prompted. So I have data that doesn't even have a question associated with it. So just for a validation check, I'm going to go ahead and view it. And if I scroll down here, oh, there you go. You can see that the questions line up. Now, not right now, due to time. Usually, though, you would go through and look at a couple of lines to make sure that it did sync correctly. So that's great, but I need to still merge them. But since we have this question ID now, and on my answer, it has that ID row, we can merge on that. So I'm going to call my nice merge function. So I say merge this df, which is my x value, and answer, which is my y. And that's why you see by.x. So it's saying, look at this one, and it's going to be with question column. And then in the y, which is answer, look for ID, and go ahead and merge on that. So we'll take the head of merged, and you can see it's all combined. And now we can actually do a ggplot. So you can see over here, this is kind of what we want to make. I want to see the incorrect versus correct, and the 4 main different types of brainwaves. So I can go ahead and throw ggplot at that, but I want to take a subset. And you'll see that here. So I'll take the subset of merge, and I say when type is equal to one of these values, then go ahead and plot it. Otherwise, ignore it. And you can see in my geom smooth, I'm saying x is equal to the negative. And that's because if you look closely here, I want to see what it looked like when what the EEG data looked like when everything was done. What was those last thoughts? Did they think they were correct? Did they think incorrect? Was there something different about it? So I run that, and I'm left with something very similar. But if you notice, the columns aren't exactly right. And this actually gave me some trouble originally, until I figured out that you can pass in functions to a wave graph labeler. I think this is a really powerful tool when you want to start doing all these different facet graphs to show a lot of data at once. So I went ahead and created this little function. So I pass in the value, right? And I'm saying if the value is equal to type, so if it's from this column, right? So when it goes to label each one of these, say it's alpha, beta, theta, and delta. And then otherwise, if it's equal to correct, so referencing this column, it's going to be now called incorrect and correct. So I save that as a function. And then I can recall my ggplot. And if you look right here, I call labeler, and then I get to call my function. And I went ahead and added some GG titles already for it. But let's see. So now we actually have a graph that shows a lot of that data and what's the difference between incorrect and correct thinking. So now it's kind of, let's go back and analyze it a bit. So immediately, what do you see? What's different between the two? So the incorrect is obviously longer. I have a lot more data that's over a longer period of time. And correct thinking was so short. And there's some questions that definitely maybe they bumped it, it got moved, the sensor got messed up, something happened there. So this isn't the greatest graph to really say, I should build a model off of these experiments. So have to go back and relook at everything. And not just for that. And the reasons that it was short was because of the test subjects remember tricks. So if you remember something of an even number, you automatically know it's divisible by 2 and not prime. And also, if you see a larger number, people are going to get scared. I know I wouldn't want to sit there and think about, is this a prime number? So they'll just randomly guess. And they could get lucky. But it also skews my data. And also the probability that the number is prime. So prime numbers follow that 1 over ln x shape. So if the number is bigger, it's probably not going to be prime. So it's just not a good experiment for me to use. So I did something that a lot of people hate me for. I made college students do 3-digit division and 3-digit multiplication problems by hand. So turns out a lot of kids, by college, don't remember how to do this problem. So a lot of people hated me afterwards for a bit. And this experiment was set up the same way. It was, I know when the problem was shown, I knew when the problem was finished. Every test subject was able to have a piece of paper and a pencil. They had unlimited time. And the majority of the test users were males between the ages of 18 and 25. And this is gathered from students that attended hackathons in the state of Florida. So I tried to get a wide variety of just not students at my school. Now, most of these students obviously were computer science, so maybe a little skewed too because they tend to know a little bit more math. But I got them to think. And the average time took was about 20 minutes, with the longest being 45 and the shortest being 7 minutes to answer all questions. Back to cleaning the data. But this time I didn't want to just visualize it. I want to start handling the model. I want to start using this stuff to see what I can predict. What can I use this data for? And that's where Python came into play. So I just had to load in the data. And the nice thing of how I set it up was if type element equals whatever I'm looking for. If I want to use the alpha waves, I can use the alpha. I just change that variable to be beta or gamma or anything I'm looking for. So this made my code really reusable. And especially if I want to use further experiments, I can continue to use that. So that's something to always keep in mind, at least for me. And so this left me with a data frame that looked like this. I had my time, and for alpha and beta and delta waves, it had 4 signals. And that's great and all, but I still needed to reassociate that with my answer. And so I used pandas, and this line at the bottom is probably the most important thing to me because it made my life so easy. So pandas has this function called dot between. So I was able to say, for this current line in my answer file, which has the time shown and the time answered, find everything for me in my views data set that matches there. So in one line, I was able to save a lot of headache for me. And that left me with a data set that looked like this. So I basically was able to say, instead of time, show me what answer, if they got it correct or incorrect for that. Now, it was time to actually do some data science and machine learning. I was really excited. So just to give you a quick background, when I first did this, Keras had just come out. It was still just getting kind of known. TensorFlow was still a baby version. So it was best to kind of use Theano. If you did a Google search at the time, everyone said, use Theano, use Theano. So I was able to actually use Graham Taylor's vanilla RNN, which I found on GitHub. And he made these beautiful classes where you can just input your parameters, and you only have to understand, you don't have to understand all of Theano to build these neural networks. But instead, you just set in the parameters and manipulate it a little bit as you need. So originally, I wanted to use raw FFT values. Because of that previous research that said wavelet was best, I was like, let me just see what happens with FFT instead. So you may be confused by the 516 input nodes. Well, for the raw FFT, for every single signal, because there was 4 of them, it had 129 when it got converted into that space. So that gave me the 516 input nodes. And I had an 80 hidden nodes layer with the 1 output layer and 1,000 epochs. Now, this is a lot of epochs. And that was one thing we kept monitoring is it overtraining itself? Is it overtraining? And it wasn't until it hit around 1,500. So we decided, 1,000 epochs gave us some of the best output. But you can't just throw out a neural network and say, look how awesome this is. Look at how well. I did it to other classifiers, too. So I used Weka when I used these classifiers. But you can also use them in scikit-learn. I just personally, at the time, had a lot of experience with Weka. So I did it on nearest neighbor, decision tree, random forest, and sequential minimal optimization. And that left me with my RNN barely outperforming decision tree and SMO. Not the greatest results. And this is kind of where I originally stopped doing some of my research. But as all these libraries developed, And as everything started moving forward, I wanted to move forward more with my research. And this is where Keras started becoming a lot more known. And it just developed so much more. And even now, just recently, CNTK is available as a backend on Keras. So it's constantly getting developed, which allows me to have my program constantly getting better. So I'm just going to show you guys a very simple Keras program to show the flexibility of how many experiments I could run without having to change a lot of my data. So this one, I'm going to use an LSTM. So an LSTM has the batch size. It needs the windowing that you want, and then how many items are at that window, at that instance. And you'll also be a little confused of the two output nodes. So I wanted to say predict if it's correct and predict if it's incorrect, and I'll take the highest one. And I'll also so I have the one layer of LSTM and then just one dense layer. So it looks like this. Now, if you see at the dense layer, let's say I wanted to output only one instead. I could change this to 1, change this to be sigmoid, and then change this to be binary cross entropy. So doing this sometimes causes a difference in how your data outputs. But in this case, it's such a simple, and there really wasn't much of a difference. And I go ahead and I call evaluate and predict. So and mostly the predict is to give me those actual Ys on my test. So I can send that into a classification report and see kind of what I get out. So with this very, very, very simple LSTM, I get something not that great. So this is currently where all my research is focused. I'm trying to figure out what brain waves are the best ones to use. What combination? Is there something I need to do differently with the brain waves before I pass it in? So this is currently where all my research is. I have tons of experiments, a list of them that I'm trying to run through. But that's great. But let's say I had a model, right? And I currently am using my previous raw FFT value. But I want to build an actual prototype with this now. So I used tkinter to actually build a system with the Muse headband developer functions. And so the actual prototype is just this little window, and it's green, as you're thinking correct. And if you start going down the wrong path and start thinking incorrectly, it turns yellow and then turns red. Nothing too sophisticated. But the actual code is really simple to build, and I won't have to do a lot of change for it. So this is the Muse, right? So it calls the dispatcher. And in here, it says, basically, look for this. When you get a signal that has this, trigger this handler. So I have 3 of these handlers, right? Basically, each one for those sensors. And it always goes in order 0, 1, 2, 3. So I know as soon as I receive signal 3, I can say, OK, now that I have an array of 516 elements, go ahead and call my .predict function. And so in my get thought, and you'll see I have my answer. And from here, I can just go ahead and update my other process, which is my actual visual. So tkinter, I had never used before, and it was actually really simple to set up. And there's a lot of documentation out there on the web if you need to make a quick GUI. So I just go ahead and call tkinter, and then add buttons, whatever you want, right? And the main thing is I just have this continuously checking color. And if I come in here, this TC, so this is my thought counter. And this is actually a shared variable between my other process, which is the Muse, which is constantly reading in the signal, and my actual tkinter process. So if you have questions on that and how to share values, I can definitely answer them afterwards when you're working with locks and everything. So I sent it up there. I have a threshold that's still kind of figuring out, where should I say, if they start thinking this many incorrect times, it should be yellow, red, stuff like that. But it just goes ahead, calls change color. And I just say change the frame background to whatever color I want. So pretty simple, but I still have a lot of next steps, and I still have a lot of development for this. So as I mentioned earlier, I wanted to determine which values or combination of values are the best. And I want to see what happens if I switched over from FFT to wavelet transform that Kierkegaard and Sherman said was the best combination for brain waves. I also just want to gather more data from more subjects. I had about 10 or 15 subjects I had to throw out because the headband ended up moving, and there was just a lot of issues with the data. And it was like, that's not really their brain wave. And also just want to further development type more. I want to put it not just on the computer, but on the phone, maybe a little vibrate instead, or those wrist watches or other devices that you can wear on your wrist, maybe a slight little vibrate instead, so it doesn't distract the user from the actual problem. So the quick references to Graham Taylor's RNN and the Muse Developer Toolkit, you can also just Google them, and it pops up. And then quick shout out to Dr. Joshua Eckroth, who was my advisor during this project and continuously still helps me. Thank you.
Great, thank you, Katie. Now, I did check partially before whether we could do this, but I'd like to invite your lovely assistant up with the headband.
Yeah, just give me one sec.
Can you get the demo going? At the very least, we are going to go back and watch his brainwaves for a bit and see just what happens when we ask different questions. While we're doing that, and while you're getting that started, we actually had one question come in online. You were talking about the range of times that it took people to answer all of those math questions, ranging from 7 minutes through to 42 minutes, I think it was.
Yeah.
Someone online is very impressed that they got them all done in 7 minutes, and we're wondering how many questions are involved. And maybe that's going to embarrass the person who took 42, but... It
was 10 questions. 5 of them were multiplication, 5 of them were division, and I'm going to give a shout out to Georgia Tech, because there was a Georgia Tech student. He didn't even write anything on paper, and he got them all correct.
Oh.
Yeah, so it was I think he was the only one to get them all correct. So, yeah, really shocked by that. That's one stood out in my brain.
Did his brainwaves move at all during that, or...?
That I do not know. I try to anonymize it. So as soon as it gets converted to CSV, yeah. I have no idea whose data is what. So you'll see, too, I'm using Python 3. So the Theano I used was actually written in Python 3. So to actually use the .predict function, I had to make sure all this was in Python 3. Sorry. Oh.
While that's going, is there anyone in the room with a question that they'd like to ask, which hopefully will not distract Katie too much? Yes?
Okay.
So the question is, what's the end goal of the overall project? Do we want to help people stop getting too far off track? It seems to me like it'd make a great lie detector.
Possibly, yeah. So, but my overall goal was I could envision this being for a classroom setting. You know, classrooms are growing larger and larger these days, and there's only one teacher in the classroom. And some students just have that struggle, and they just need someone to kind of be like, you're going on the right track or you're not. And that helps them get through the problems. So these are becoming so much cheaper as the day goes on. So if there's something that we could bring in and kind of supplement these teachers and supplement these students. But eventually I would like to also include language. So this is very mathematical based. So that could be applied to someone studying for the LSAT, which is very logical. So we'd like it to eventually get there, but it'll take some time. Oh, okay.
Is TK Inter not showing us any love today?
No, it's not, and this is why I was concerned about.
This is why originally she wasn't going to do the demo, and I had to talk her into it. So this is mostly my fault.
I didn't check it before I ran it. So kind of just give you an idea of what's going on. So the Muse can be ran on 2 things. If you're going to use the Muse Lab, it does it through TDP, I believe. And if you're going to use it through like any device you want, it has to go through UDP. So you might see like, oh, an error going on, but that's perfectly normal for the device. Oh.
Are there any other questions from the room? Are there any TK Inter experts in the room?
It's bash to, it's a connection because I'm running in the bash, yeah.
Okay. Sorry, question?
Yeah, I was wondering whether the training of the network assumes that everybody has the same sort of relationship between brainwaves and performance.
And that was part of the experimentation is there a way that, is there a pattern of the oscillation from the brain waves that we can understand that maybe someone's brain waves occurs a little bit higher in the frequency or lower, but is there an overall pattern that we can use to predict of incorrect data? So the actual getting into more of the neuroscience, I can't talk too much about, but that was my overarching goal.
So as a goal, but in order to get this far, you had to assume one way or another that
Yeah, so it was kind of a leap of faith, kind of
that
to,
basically people's brainwaves are interchangeable.
yeah.
Or at least within the bounds of a machine learning algorithm that's going to hopefully take enough samples in the training set to be able to get enough similar characteristics between a range of people. If this is not going to work, can we go back to the original chart and just ask him questions? And...
Well, okay, I was going to try one more thing. I don't think I have it.
Because I think we've got a room full of people who want to ask really difficult questions and watch someone's brainwaves, right? So start thinking of questions. It's not every day you get a chance like this, right? This is what you come to PyData for, people. Hey, what's your name? Come around here.
Hello, I'm Angelo.
This is Angelo. Angelo is our
There we go.
beautiful volunteer today. He's going to stand here with the brainwaves running on the screen, which is it's a little bit, it's got to be awkward for you, surely. I mean, it's
This is just a normal day for me.
normal day for you?
Yeah.
Oh, good. Because I know a lot of people have that fear of standing up on stage and being naked, and this is...
No, this is what it looks like, yeah.
It's actually happening to Angelo. Okay, does anyone... and so, okay, we can already see stuff happening there. It's like when he laughs, that white, the second line down
Yeah,
is bouncing
so
a bit.
there's a little bit of background is that there's an accelerometer here, so it does track whenever I move my head, but then you always want to look at the green and the orange lines.
Okay, green and the orange lines are the interesting ones
Sounds
for if we ask you difficult questions. Or to see when you're lying. So what was your name again?
Justin.
Oh, you had to work hard for that one. Look at the green line. Good. Can we try that one more time?
Angelo. Yeah.
Angelo. Oh, there we go. No,
Yeah, so
totally honest.
working as
completely
intended.
honest. How have you enjoyed PyData so far?
I totally hated it.
We're going to end the session right now.
That probably was a joke.
Which session was your favorite?
Actually, I really enjoyed the Of Mice and Men one. That was a really interesting one. Now it seems ironic because I'm the mice now, so.
So he identifies with the mice from the Of Mice and Men session. We should probably grab your microphone, shouldn't we? We've got a handheld right there. Sorry. This is fun. Does anyone have a question for Angelo? It'll be on in a second.
All right,
Now
cool.
it's on.
Hello? Hello? Oh, cool.
347 times 575.
575. Wow, that's. Ugh.
That was hard work just repeating the question.
I can get back to you that one later. Probably. Ooh, that's a.
Tabs or spaces?
All right, so I'm gonna cheat a little bit. Non-breaking tabs, like you set tabs to spaces. Yeah, I know. See, if I tell you guys what editor I use, you guys are probably not gonna like
He
it.
didn't even flick for that. What editor do you use?
VS Code. So. Yeah.
That's totally okay here.
Oh, cool.
You can see the relief. You can see the spike of relief.
Yeah. That's what relief looks like.
Anyone else want to ask Angelo?
Python editor.
Oh, excuse me?
What's your favorite Python editor?
All right, you guys are gonna hate me, but I actually don't use Python as my primary language. Ironic, because I'm wearing the shirt. I know, that's...
Here, though.
That's why you're here. We can fix that.
If I was to pick, I would pick PyCharm.
Okay.
Yeah.
Same here.
Okay.
You're welcome.
Not VS Code?
No,
No, not yet.
I would use an IDE to hold my hand first before I, and then, yeah.
Okay. Anything else from the room? Anyone else want to? Yes, Brett Cannon.
Excuse me? How long how often? Oh, this is actually my first time forced to.
Second time.
Yeah, second
Second
time.
time.
Yeah, so I had to think about that.
He was going on the wrong track.
Yeah.
And something buzzed and sent him back on the right track. All right. Do you think you'll come back to another PyData after this
Oh,
experience?
of course, if you guys will have me back again.
Well, absolutely happy to have you back again. All right. Let's thank Katie and Angelo for the session today.
Not for me, it's for her.
We're going to take a short break here. Live stream's going to get some closing notes, but then everyone will be back in this room. We're going to have lightning talks. They're going to be a lot of fun. We've got 10 short 5-minute talks coming up. It's going to be really exciting. So we'll see everyone back here in the room in just a few minutes, and live stream is going to close out. We'll see you guys later. Thanks for being at PyData.